We learned a little bit yesterday about the Bohr model of the atom, our third model of the atom. Remember, the first model of the atom was the Dalton solid sphere model of the atom. There really wasn't much to that. The atom is an indivisible solid sphere. And then we talked about the Thomson plum pudding model, which was an acknowledgement that there was something smaller than the atom itself. The atom consists of a sea of positive charge with a bunch of little electrons floating around inside it. Then we looked at the Rutherford planetary model of the atom, which said the atom consists of mostly empty space with a small, dense, positively charged nucleus in the middle and electrons orbiting around. But then yesterday we talked about our fourth model of the atom, the Bohr model of the atom, which is a lot like the Rutherford model of the atom, but is distinguished from the Rutherford model of the atom in three ways. If I had to summarize these three things that distinguish the Bohr model of the atom from the Rutherford model of the atom in one word, what would that word be? A single word that can kind of summarize all three of these things. Okay? Levels. Levels. Electrons exist not just anywhere around the nucleus, but they exist on levels. And each level is characterized by a specific amount of energy. So the energy of this level is a certain value. If you get two electrons on that level, they have the same energy. If electrons are on a different level, well then they've got a different amount of energy. Every level is characterized by a specific amount of energy. Now, each of the electrons on each of these levels are in what we call a stationary state. A stationary state is this idea that these electrons are kind of exempt from the classical laws of physics. Maxwell taught us over 100 years ago that accelerating charges generate electromagnetic radiation. Well, these charges, as they orbit around the nucleus, are accelerating. They experience centripetal acceleration toward the center of the circle, but they don't emit EMR. If they did, we saw yesterday that they'd spiral into the middle. Well, they don't emit EMR. So it's as if they're not accelerating. They are, but it's as if, Kaylin, they're not accelerating. It's as if they're not moving. It's as if they're stationary. They're in a stationary state, like they're not accelerating. Okay? Yeah, go ahead. And finally, the third thing talks about, once again, about electron levels, but it talks about transitions of electrons from one level to another. We know that electrons can go from a low level to a high level. They can jump levels. When they do that, they need to absorb energy. What form of energy is that absorbed energy usually in? What kind of energy do they usually absorb? Usually it's a photon, right? Usually it's light, although it could be some other source of energy as well. Usually it's light energy, EMR, that the electron absorbs to cause it to jump from a low level to a high level. But it can also fall to a lower level from a high level. As it falls from a high level to a low level, it will give off energy, and this time the energy will always be electromagnetic radiation. A photon will always be released when an electron goes from that high level to a low level. We showed you some pictures yesterday of some of those transitions that can take place. The first diagram that we showed you was just a reference diagram. That's the one that showed us what happens when we have a solid that's hot, or a liquid that's hot, or a gas under high pressure that's hot. That releases all types of radiation, all types of light. It produces white light, right? If I was to stand right here, in between the light and the diffraction grating, I would see white or kind of yellowish light, right? But if I allow that white light or yellowish light to pass through a prism or a diffraction grating, then it's going to split that light up into a spectrum, a continuous spectrum. If it's a prism, it produces Roy G. Biv. If it's a diffraction grating, it produces Vib-Yor, right? The backwards, the opposite of it. If it's a prism, it produces one spectrum. If it's a diffraction grating, it would actually produce a central maximum, and then a first order continuous spectrum, and then a second order continuous spectrum, multiple spectra, right? Like we saw in our last unit test. But the bottom line is the basic pattern is the same, prism or diffraction grating. Continuous spectrum, all the colors of the rainbow. What happens if I have a hot gas, this time under low pressure? Low pressure, low density. Well, this time we get light produced, again, that appears to be white light. If I stand right here and I observe the light coming from this hot gas, it would appear to be probably more or less white light. But if I run that through a prism or diffraction grating, this time it doesn't produce the continuous spectrum, because in reality, even though it appeared to be white light before it went through the diffraction grating here, it was really just specific colors of light, specific photons, okay, discrete colors. When we shine it through the diffraction grating of the prism, we see this, what we call a line emission spectrum. There's a red line right here, an orange line, a couple of green lines, a blue line, and so on. Each of these lines correspond to individual photons that were released during individual transitions from high levels to low levels. So in this hot gas, there was a transition of an electron from here to here that released this photon. Another transition that released this photon, and another one that released this photon, and so on. That's what we're seeing there on this line emission spectrum, are the photons that are released from these transitions from high to low levels. We talked yesterday about this being kind of a fingerprint, right? This line emission spectrum looks a lot like the line emission spectrum for other elements, but just like your fingerprint looks a lot like the person beside you, their fingerprint, they look a lot the same, but they're not the same. Okay, the spectrum produced by this hot gas would be slightly different or much different than the spectrum produced by some other hot gas. Because they're all different, we can identify the unknown gas based on its spectrum, just like we can identify who's ever at the crime scene based on their unique fingerprint. Well, what happens if we go back to a solid or a liquid or a hot gas under high pressure again? Stand right here, get rid of the cold gas. What do I see? I see white light. Pass it through the prism or diffraction grating, I see the continuous spectrum, all the colors of the rainbow. But now what we're going to do is introduce this cold gas, which is going to absorb some energy. The electrons in this cold gas, when they absorb energy, jump to a higher level. They go up to a higher level. And as they do that, well, we don't have the continuous spectrum anymore. We have a continuous spectrum minus the photon that was absorbed. As I stand right here, it appears to be white light again, and it is almost white light, but in reality, it's white light minus a few photons that were taken away by the cold gas, causing the electrons to be energized in the cold gas. What do you notice about these two spectra? Exactly opposite, right? We know that the spectrum is a fingerprint for whatever element you're dealing with. The emission spectrum and absorption spectrum for a particular element will be the exact opposite of one another, though. Okay? Make sense? We use this all kinds of realms, but we talked yesterday about the astronomy application where you're examining something from space that's producing light, and you want to find out what it consists of, what the composition of it is. Look at it through a spectroscope and observe the spectrum. Okay, if it happens to be this spectrum that's produced, then it tells you that, well, that star must be made out of that gas, that element that produced that gas, or that produced that spectrum. All right. Today, what I want to do is take a look at what we call electron level diagrams. Electron level diagrams give us a little bit more information here. This is for hydrogen, by the way. Although you can have electron level diagrams for any element, and they're going to look more or less the same. What's going to be similar about it? Well, the spacing of the lines. Each of these lines, by the way, corresponds to an electron level. This would be the nucleus down here. The ground state would be the first level past the nucleus, then the second level, then the third level, then the fourth level, and so on and so on and so on. The basic structure of an electron level diagram is going to look the same no matter what element you're dealing with. Hydrogen, sodium, calcium, lithium, whatever the case may be. You're going to find that the closer you are to the nucleus, or the closer you are to the ground state, the further apart they are. The higher you get, the spacing gets closer and closer together. You're going to find that no matter what element you're dealing with, the difference in energies between the levels keeps getting smaller and smaller, which is proportional to the spacing. Differences? What are you going to find? Well, for hydrogen, we have specific names for specific series of transitions. If an electron is making a transition from any level to level 1, we call it the Lyman series. You don't need to know that name. If it's necessary to know that, it'll be given to you on your test. It wouldn't be called the Lyman series for any other element, though, just for the hydrogen atom. The Balmer series is when we're going from one level to whatever level to the second level. In the Paschen series to the third level, and the Bracket series to the fourth level, and so on. We used to have to know these. And we used to remember that by remembering a little mnemonic device. Lyman, Balmer, Paschen, Bracket, little boys play baseball. Little boys play baseball. Helped us to remember which one went where, right? In the end, you don't remember that, that's okay. Okay, do remember though that electrons can make transitions in a particular series to the first level or to the second or to the third and so on. Okay, these names are different for different elements. The energies are also different. You know that the differences in energies are consistent from one element to another. Okay, the spacing gets smaller and smaller and smaller as they go up and up and up, but the actual values are different from one element to another. You get another diagram that's not for hydrogen, don't worry about it. Just look at the numbers that you're given and deal with it in the same way as we're going to deal with this diagram today. Just that your numbers will be different, as they always are, right? From one example problem to the next, the numbers are always different. All right, what are we going to get from this? Well, honestly, we don't really care what the energy of a particular level is. The energy of the third level is negative 1.51 electron volts. We don't really care. We always care about, in physics 30, the difference between two levels. The difference between two levels. You will never use by itself, in physics 30, this number, or this number, or this number. You will always, when you see one of these diagrams, subtract two numbers. Okay, always subtract one level from another. You'll see in a minute what I mean by that and why you would end up subtracting two particular levels. Finally, one more thing before we do an example here. Anybody want to take a stab at why these are negative values? Anybody notice that? We get negative values of energies here, and they get higher as you get closer and closer to the nucleus. Chase? It's absorbing energy, so electrons are absorbing energy. Well, they can absorb energy. When they absorb energy, they go to a higher level right here. They get closer and closer to zero. So they're a negative value, and as they absorb energy, these are emission, right? As they absorb energy, they get closer and closer to zero here. Let me give you a little bit of an analogy here, actually. Let's say this is the Earth, and here's the core of the Earth. Okay, the core, the center of the Earth, the core of the Earth. And let's say you are standing, Chase is standing on the surface of the Earth, right here. He's out of the Earth. He's not in the Earth. He's not part of the Earth. He's left the Earth. He might have been down in the Earth. He dug a hole, whatever. He's out now. Okay? Chase, what's your potential energy? What's your gravitational potential energy there when you're on the surface of the Earth? Yeah, I'm probably going to say it's zero, right? Now, we can define it relative to whatever we want, but usually it would be defined relative to the surface of the Earth. So we'll say zero there, okay? Now, if I climb a ladder, or if Chase climbs a ladder up into the sky, its potential energy becomes positive something. That's not what we want to do. Chase is going to climb a ladder down into the Earth. He digs a big hole and goes down into the Earth. As he does that, his height becomes negative. So his potential energy relative to the surface of the Earth, to the outside of the Earth, becomes negative values. And the closer he gets to the core, it becomes bigger and bigger and bigger negative values. So here it might be negative 10 joules. Here it might be negative 15. Here it might be negative 25 joules. Does that make sense? As your height becomes a bigger negative number, your potential energy becomes a bigger negative number. Well, let's pretend that this is not Chase outside of the Earth. Let's pretend that this is an electron outside of the atom. it's left the atom. We're going to define its potential energy as 0. And the closer I get to not the core, but the nucleus, the energy becomes larger but negative. So let's go back to this picture again. Here's Chase outside of the Earth, or the electron outside of the atom. We say it's at the infinite level where the electron is free. Its energy is defined as 0. But as I climb down that hole toward the center of the Earth, the core of the Earth, or as the electron climbs down that hole towards the nucleus, its energy becomes bigger as a negative value. Does that make sense? We could have defined these as positive, but that's just not the way it's done. By convention, they're defined as negative values. It's arbitrary, but it is what it is. Okay, we got to do the standard. Okay, even if it seems silly, it is what it is. Okay. All right, let's do a couple questions here. The first question that's in your notes here, you don't have to copy this down, says, using the diagram above, determine how much energy is emitted in the second line of the Balmer series in the hydrogen atom. The second line of the Balmer series. Well, I told you, you guys don't need to know what the Balmer series is. The good news is, in this diagram, we're told what the Balmer series is. It's electrons making a transition from a higher level to the second level. The second line of the Balmer series is this one. This is the first one. This is the second one. And that's a transition from level 4 to level 2. If I want to find the energy of that transition, all I'm going to do is subtract the two energies. The second energy level minus the fourth. The final minus the initial. And when I do that, I get negative 2.55 electron volts. When energy is emitted, and that's what would happen here, right? Energy would be emitted or released. It would be a negative value. And in this case, the photon that was emitted would have an energy of 2.55 electron volts. Usually, we end up dropping that negative. If this is a multiple choice question on a test, they're probably not going to have the negatives in front of it. Usually, it's just a magnitude we worry about. That's easy enough, right? Notice we didn't use this value on its own or this value on its own. We found the difference between them. That's what we always do, right? Always find the difference between two different levels, whether it's hydrogen or any other element. Let's do another one. Using the diagram above, determine the ionization energy for an electron on the first level of the hydrogen atom. What does that mean, the ionization energy? What does it mean to ionize a hydrogen atom? Take an electron away? Yeah, charge it. Take an electron away. Leave it positive, right? H plus. Well, if the electron is on the first level, if we want to ionize it, we got to get it to the infinite level, to the surface of the Earth, right? Outside of the Earth, outside of the atom. So in other words, we got to go from level 1 to level infinite. We have to subtract 0 electron volts, our final energy, minus negative 13.6 electron volts, our initial energy. And when we do that, we end up getting positive 13.6 electron volts. It becomes a negative when you're going down or releasing energy. It's a positive when you're absorbing energy or going up. So the photon absorbed here would be positive 13.6 electron volts. That would get rid of an electron. That would cause Chase to climb up the ladder from the center of the Earth to the surface. Same thing, right? Except this is positive instead of a negative value. Different numbers. One more. How much energy must a hydrogen atom absorb in order for its electron to move from the ground state to the n is equal to 3 energy level? From ground to n is equal to 3. So we're going from level 1 to level 3. We're going to subtract negative 1.51 minus negative 13.6. Okay, it's the final minus the initial. And when I do that, I'm going to get positive 12.09 electron volts. I've absorbed, or the atom, the electron, has absorbed 12.09 electron volts to cause this transition to take place. If it gave off 12.09, it would have caused this transition to take place, emitting a photon instead of absorbing a photon. Here's one for you. What if the photon that goes through this gas, the light that goes through this gas, doesn't have quite that much energy? What if it has, what if I've got a photon with 12.05 electron volts of energy? What's going to happen? So you got this gas, this light is passing through this gas, and each photon of light has an energy not of 12.09, but of 12.05. Is anything going to happen? And if so, what? Can the electrons absorb that energy and go up to here? No. Why not? Because they needed 12.09 to go up to there, right? How much do I have? 12.05. A large Slurpee cost me $2.30. If I go to the store with $2.10, they don't round up. They don't say, yeah, it's close enough. Here's a large Slurpee. What do I got to do? I got to buy a medium Slurpee, right? I got to get the next biggest Slurpee because I don't have enough to get the large Slurpee. It doesn't matter if I cost $2.30. If I have $2.25, they don't round up. I got to get the next biggest Slurpee. Even though the next biggest Slurpee only costs like $2.10, I got more than enough to get the next biggest one, but that's all I can get. I can't go beyond what I have. Okay, if I need 12.09 to go to here, and I only have 12.05, I've got way more than enough energy than to go there. Way more than enough. But that's as far as I can go, because I can't go to the next level without having a little bit more energy. It doesn't have to match up perfectly. Okay, the energy difference between level 1 and level 2 is 10.2 electron volts. Okay, all I need to go from here to here is 10.2. But if I have 12.05, I can still go from here to here. I just have a little bit of energy left over. Get to put it in my piggy bank when I get home. But I can't go to the next level unless I have enough energy to go to the next level. And it's not just a matter of, oh, it's really, really close. It rounds to that. Okay, we can't do that. One more thing there on this example, okay? I'm going to extend this a little bit. We said that it was, the energy absorbed was 12.09 electron volts. What if the question said, what's the frequency of the photon absorbed? I mean, it was a photon that caused this to jump to a higher level, right? Or at least most likely. What's the frequency of the photon that was absorbed, or what's the wavelength of the photon that's absorbed? This is the energy of the photon. If I want to find the frequency, all I'm going to do is set that energy equal to h times f. If I want to find the wavelength, I'm going to set it equal to hc over lambda. All right? Remember, you're never going to use the energy of a particular level. We don't want this energy or this energy. We never set that equal to hf or hc over lambda. We want the difference between those two levels. We want the 12.09, not the negative 13.6. Okay, the difference in energy is equal to hf, hc over lambda. All right, I'm going to give you a couple minutes to work on two questions here on page 775, but I'm going to extend those just like I did my example question, okay? In the first question, we're absorbing energy to cause the electron to jump to a higher level. I want to know the frequency of the EMR that I need to absorb. In the second question, we're releasing energy because we're going from level 5 to level 2. We're emitting a photon. What's the wavelength of the photon emitted? You're not changing the questions 1 and 2. All you're doing is adding to them. You still got to find the energies, just like you did, just like they ask you to do. I'm just asking you to find something beyond the energies. That's all. If we're okay with those questions, then I want to take a look at one last model of the atom. We've taken a look at the Dalton solid sphere model, the Thomson plum pudding model, the Rutherford planetary model, the Bohr model of the atom. Now our fifth and final model of the atom, the one that was devised almost 100 years ago, and we still believe to be correct today. We call it the Schrodinger model of the atom. Sometimes we call it the quantum mechanical model. Sometimes we call it the electron cloud model of the atom. Be prepared to see any of those names. They all mean the same thing. Now, the Schrodinger quantum mechanical electron model of the atom says that the atom does consist of a small, dense, positively charged nucleus. Now we know it consists of protons and neutrons, and that there's electrons orbiting around it. But those electrons were a little less certain than we thought about the location of those electrons. In the Bohr model of the atom, we said that they were orbiting around on very specific levels. Now, they still do, but those levels don't have a specific position. They have a specific energy, but not a specific position. Rather, we'd now say that these electrons are kind of orbiting around within a cloud somewhere, hence the electron cloud model of the atom. The reality is these electrons, as they orbit around the nucleus, are orbiting around as waves. Remember the de Broglie hypothesis? Particles like electrons have a wave nature. Well, they're orbiting around the nucleus as waves. They don't have a distinct position until we observe them. We can make a prediction as to where we might observe them, but in the end, it's only a prediction. And just like with another quantum process that we talked about, being radioactivity and half-life, we don't know for sure what's going to happen. We make predictions based on probability, but we don't know for sure exactly what's going to happen. If we had to make bets on it, if we had to put money on it, we would predict the location of an electron to be wherever Bohr said it was. Bohr would have calculated the radius of the orbit of an electron, and if we are making a prediction as to where we're going to find that electron, then we would make a prediction that the most probable location is where Bohr said it was. But it doesn't mean necessarily that it's going to be at that spot. It could be anywhere within this cloud. And this cloud is big. Okay, it ranges from a tiny little bit to a lot. It's kind of like this. Jotham gets in a fight, okay? And I say, Jotham, go to the office. Okay? And Jotham, I say, go see Mrs. Staffichuk. And Jotham says, okay. Where does Jotham go to see Mrs. Staffichuk? Goes to her office, right? Why does he go to her office? Even though I just said go see Mrs. Staffichuk, because the most probable location of Mrs. Staffichuk is in her office. Odds are that's where she is. Does that mean that's where she is for sure? No, she could be down the math wing. She could be down the science wing. She could be in the social wing. She could be outside getting something from her car, although there's a smaller probability of that. She could be at her house because she forgot something and she had to drive back to her house, although there's an even smaller probability of that. She could be in Calgary picking something up for grad, although there's an even smaller probability of that. She could be on a flight to Mexico right now, although there's an even smaller probability of that. I don't know why she'd want to go to Mexico when it's so hot outside, but there's an actual possibility that she's in any of those locations. But the further away she gets from her office, the most probable location, the probability decreases. So, same thing with electrons. The most probable location that we're going to find them when we observe them and the wave function collapses is where Bohr predicted they would be. But there is a real probability that they could be anywhere else. It's just that the further away we get from Bohr's prediction, the less probable we're going to find that electron at that position. Does that make a little bit of sense? It doesn't have to make perfect sense. Quantum physics never makes perfect sense. We talked about the electron being in two places at the same time and interfering with itself and producing the wave pattern. Remember that video, that cartoon video I showed you? That doesn't really make sense. It doesn't have to make perfect sense if you can kind of just get the gist of it and kind of get a taste for it. So, bottom line is this. What we're doing here is kind of almost, we're taking a step forward by taking a step back. We were certain about where we'd find the electron. And now we're certain that we can't know where the electron is. Does that make sense? We now know less, but we know more about what we can't know. We can't know where the location is until it's observed. We can only make predictions. But we know that we can't know. And before, we thought we knew where it was. We didn't know that we couldn't know where it was. That probably makes you even more confused, eh?